Hello, this is Truth Socrates. Welcome to our 14th video in multivariable calculus, known as Math 5C at Pasadena City College. So in our last video, we introduced polar coordinates with the goal of eventually setting up integrals in polar coordinates and computing them. And that is, of course, what we are going to do in this video. However, before we get there, we're going to do two things. While we're on page 1 of this PDF, we're going to review how to construct the definite integral back in basic calculus. And then we're going to review what we did in our previous video, because we're going to use some of that to construct and set up the double integrals that we're going to see today. So when we did the definite integral in basic calculus, remember these are the basic steps, right? We have an interval a to b, the domain of our continuous function. And the first step is to divide that interval into several pieces, okay? So each piece has width delta x, and that's b minus a over n. And that creates a partition on your domain from A to B, okay? So the definite integral, of course, is the limit of this Riemann sum. We have a similar definition for a double integral, where we have a double limit of a double sum, and we have not just delta x, but also delta y. And our function is in two variables, x and y. So let's go over to that definition and we'll review it. All right, so here we are. We also have a delta y, and if our domain is from c to d, then our delta y is d minus c over n. And I guess we use the letter m now for our delta x, okay? So we have a partition along the x-axis, a partition along the y-axis, and we get these subrectangles. And within each of these subrectangles, we pick a representative point, Pij, and that is the point that we use to compute our function, f of xy. And then we have there it is, we have a double limit of a double sum, and that is our function evaluated at the representative point. Take that double limit, and that becomes our double integral. So today we are going to apply this now to a polar rectangle, which will be the domain of our function in two variables, okay? So that was one of the things that we saw yesterday in our last video, where we saw domains which are described as polar rectangles, where r is within a and b, and theta is between alpha and beta. So let's review that. Let's go back to our to what we did in our last video, where we introduced polar coordinates. Okay, so we talked about the polar coordinate system. We saw how to change the grid in GeoGebra so that it comes out in polar coordinates. We plotted several points, both with a positive radius and with a negative radius, okay? And of course, we learned how to plot the angles, whether they are positive or negative. We go counterclockwise or we go clockwise. And then, very important for today, we have conversion formulas, okay? So if you want to convert x and y into r and theta, we are going to replace x with r cosine theta and y with r sine theta. In many of the integrals that we will encounter, x squared plus y squared will show up, okay? So we have, that's simply r squared. Okay, and then we looked at polar rectangles, and these are going to be the domains of our double integrals in this video, okay? So we have a full disk. R goes from 0 to 2, theta goes from 0 all the way to 2 pi. If you only want the upper half, then you only go from theta is 0 to theta is pi. If you want the quarter in the first quadrant, theta will just go from 0 to pi over 2. And we also saw annuli, plural for annulus, and it's basically a disk with an inner disk removed from it. Okay, so in this case, r goes from 2 to 3, theta goes from 0 all the way around to 2 pi. And we saw this one, the right half of the annulus, and we have theta going from negative pi over 2 to positive pi over 2. Here's a more general annulus, and we're going to see something like this when we talk about partitioning our polar rectangle. And later on, I'm going to give you an example of a double integral where our domain is going to be the upper half of an annulus. Okay, so when that happens, of course, if you only want the upper portion, theta will go from 0 to pi, kind of like how you have the upper half of a disk. Okay, so we're going to continue now with subdividing a polar rectangle. All right, so here's the reason why I wanted to review with you the partitioning of a regular ordinary rectangle into subrectangles when we introduced the double integral. Because we're going to do something similar today. The algebra looks the same, but the geometry is going to be very different, as we are about to see. So we have a polar rectangle where r goes from a to b and theta goes from alpha to beta. Same first step. We're going to partition a to b into m equal pieces, but it's along the polar axis. And you might think, well, isn't the polar axis the same as the positive x-axis? Yes, but now when we actually partition AB, they're not x-coordinates only. They are r-coordinates. Okay, so one thing at a time. We have delta r, b minus a over m, and we have the partition. r0 is a, the left coordinate, and then we have r1, which will be a plus delta r, r2, a plus twice delta r, just like before, all the way up to rm, which will be the right endpoint, b. Instead of vertical lines, though, these numbers are going to produce circles, and the radii, plural for radius, of these circles will be r0 through rm. Okay, all of them centered, of course, at the pole. So what about alpha to beta? Same idea. We will divide it into n pieces, each piece of width delta theta, which will be beta minus alpha over n. Okay, so again, this will produce a partition where now theta 0 is the left endpoint alpha, and then we have theta 1, theta 0 plus delta theta, theta 0 plus twice delta theta will give you theta 2, and so on, until you get to theta n, which will be the right endpoint, beta. So why don't you just show the picture? Okay, here is our picture. So in this picture, what we did was we have a polar rectangle, r going from 2 to 3.5, and theta going from pi over 12 to 5 pi over 12. Okay, so why funny numbers? Well, I wanted to subdivide into 3 pieces along the polar axis, so our delta r is just 1/2. Simple enough. But along the, in the theta, for theta, I wanted to divide into 4 pieces, okay? So 5 pi over 12 minus pi over 12, 4 pi over 12, also known as pi over 3. Divide that into 4 pieces, so each opening is pi over 12, okay? So actually that's pi over 12, this much, and then another pi over 12 makes pi over 6, and then another pi over 12, that's pi over 4, oh yeah. And then another pi over 12, that's pi over 3, and then finally to 5 pi over 12, okay? So as you can see, maybe we can see better if we zoom in a little bit. As you can see, the rectangles, the polar subrectangles that we get are not the same size, okay? They're narrower when you're closer to the pole, and the further out you get, the wider they get, okay? So when we set up the double integral several videos ago, we had delta A is delta x times delta y, okay? There's no more delta x, delta y over here, okay? We have delta theta, which is an opening, an angle, okay? What is the angle made by each of these rays with respect to the next adjacent ray, okay? And we have delta r, okay? How far apart are these circles, okay? So we're going to find out how can we compute the area of each of these subrectangles. Okay, so in order to find the area of these subpolar rectangles, which we call r sub ij, we're going to need to know where each of these subrectangles are located. So to kill two birds with one stone, we are going to use the next step in constructing the double integral, which would be to choose a representative point inside our polar subrectangle. So I believe that when you did your homework for approximating a double integral, we used the midpoint approximation, okay? So we're going to do almost something just about the same, at least as far as the algebra is concerned, maybe not the geometry. So we're going to find the midpoint of the r subinterval and the midpoint of the theta subinterval. Okay, so just take the average of the endpoints. Okay, so that will be our representative point. And let's look at the picture. Okay, so there we go. It's literally the middle. Okay, so your average theta value is bisecting the angle from theta I minus 1 to theta, and your average r value is bisecting the distance between the inner circle and the outer circle, okay? In this case, they're just subarcs, okay? So let's talk about area, okay? If you zoom in, okay, and that's what we have over here, okay, maybe tilt your head this way. Notice that the subarc on the top and the subarc at the bottom, well, they're different lengths, okay? But they are almost the same, okay? So what we're going to do is, imagine sort of just straightening out this polar subrectangle, okay? So this edge is already straight, so imagine we're going to keep that, okay? So of course, that distance is our delta r, the same length over here. But what are we going to do? We are going to straighten out this curve, and make them perpendicular to this side. Okay? Yeah, right now that is a right angle, okay, because this is a radius of the circle. Okay, so geometry tells us that that is a right angle, that is a right angle, but we need to bend this arc so that we're going to straighten them. Okay, so what would be a good length for these two sides if we're going to make them equal and we're going to make it a rectangle? Well, wouldn't it make sense to use the average width, which occurs when your arc passes through the representative point? Okay, well, what's the formula for arc length? If you remember your geometry, it's something like S equals R times theta. Okay, theta is the angle subtended by the arc. But in this case, our notation for the angle subtended by the arc is our delta theta. Okay, so our radius, our r, is our average R, which is Ri bar, what we defined up here. Okay, so the arc length formula says that this arc length that passes through the representative point will be Ri bar times delta theta. So that will be our length also for this rectangle, or I should say the width. Okay, and the height, of course, is our delta R. So put them together. The area of that subrectangle will be the width times the height, delta R. So the width is the arc length, Ri bar times delta theta, times delta R. Now it's going to look better if the delta R is next to the Ri bar. Okay, so we're going to put the delta theta outside. All right, so finally, after 16 minutes, we are now able to set up a double integral in polar form. So yeah, this might look familiar because that's exactly the same formula that we had for a regular double integral. Okay, so let's summarize what we did so far. We subdivided AB into several pieces, each of width delta R, and similarly alpha beta into several pieces, each of width delta theta. We picked as our representative point in the Rij subrectangle, Ri bar, theta j bar, the midpoints. And so what we're going to do is we are going to use those coordinates to go back to Cartesian, xy. Okay? Except, of course, in our double integral, our representative is called xij, yij. So xij is Ri bar cosine theta j bar, and similarly yij is Ri bar sine theta j bar. Okay, so that is what we're going to substitute into the definition for the double integral over an ordinary rectangle. Okay, so that's our formula. We plug in xij, yij over here, and what we see is, well, doesn't this whole thing look familiar? If we squint it, it's almost like two symbols, okay? Those symbols being x and y, except, wait a minute, those symbols are now r and theta, okay? So think of this whole function, which includes the Ri bar, as a function of two variables, r and theta, okay? So what we have here by Fubini's theorem is just an iterated integral, where theta is going from alpha to beta, r is going from a to b. We have our function where we substitute r cosine theta for x, r sine theta for y. We have an extra r in our integrand, okay? And that comes, of course, from this Ri bar, okay? So that is our inner integral, dr. Our outer integral is in d theta, okay? So there are a few steps that you need to remember when we execute this double integral, okay? So our limits, of course, will not be x and y anymore. Theta will be on the outside. I would like to say 99% of the time, but seriously, it will be like all the time, okay? R will be inside because in the next video, we are going to generalize this a little bit. It's a long topic, right? This is already our second video. There will be a third video all about polar coordinates, okay? So for now, our R will be constants from A to B. In the next video, they will depend on theta. Okay, so convert x and y into R and theta using our conversion formulas. Don't forget the extra factor of R, all right? You forget that, messed up completely. And as usual, perform the inner integral first, and then after you plug in the endpoints, you will get only cosine theta and sine theta, and you can now compute the outer integral. Okay? Now, if you see x squared, y squared, xy, you will see cosine squared, cosine cubed, same thing with sine, okay? When you see powers of x and y, right? So if that happens, quick review of basic calculus, you can use the power reduction formulas, okay? Change cosine squared into 1 plus cosine 2 theta over 2, and similarly for sine squared, except you have a minus over there. And if you've forgotten where they come from the double angle formulas for cosine 2 theta. Okay? If you see cosine cubed, you can actually get away with u substitution and a little trick. Okay? So if you have cosine cubed, for example, borrow a single cosine and then change the cosine squared into 1 minus sine squared. Okay? So when you distribute that, you will just get a cosine for the first term, and then you're going to get sine squared cosine for the second term. All you have to do is a u substitution. Okay? So with that in mind, you might want to write this down, but it's okay if you forget. I will remind you when we do our computation. Let's go to scientific notebook, and we will perform a double integral in polar coordinates. Finally! Okay, so here's the problem. We want to find the exact value of the double integral over d of 5x squared plus 7y squared minus 4y dA using polar coordinates. And d is the portion of the annulus where x squared plus y squared is between 9 and 25, and y is at least 0. Okay, in other words, it's the upper half of this annulus. Okay, so I hope you don't mind. I have the template over here. It takes a while to enter these symbols. So remember, theta is on the outside, r is on the inside. Don't forget the extra r. Okay, so I always have that here. It's built in, so I don't forget it. Okay, so let's begin. We need to express this annulus, this portion of the annulus, in polar coordinates. Okay, so, well, let's start here. Okay, so x squared plus y squared is r squared. R squared is between 9 and 25. So it looks like r is going to be between 3 and 5. I said 5. Okay, so what about theta? Okay, we want y is at least 0. So I mentioned this earlier. We want the upper half of the annulus. Okay, so theta is going from 0 to pi. Okay, so that is our domain for theta. All right, and yeah, maybe let's blow this up. Sure, there you go. You can see it a little better now. Okay, now we want the function 5x squared plus 7y squared minus 4y. Okay, so we need our conversion formulas. 5x squared. So x is r cosine theta. We're going to square that whole thing. Plus 7y squared. 7 quantity r sine theta. Square that whole thing. Minus 4y. Minus 4r sine theta. Okay, there we go. So now we are going to perform the squares. So of course that turns into 5r squared cosine squared. Also, it looks better when the square is next to cosine. Square, square, no square on the last term. Okay, so that's important because there's another r here. Okay, so yeah, it's easy to misaccount for that. Okay, so that r, we're going to multiply it in. It'll be a cubed and cubed, and now a square. Okay, there you go. So what do we say when you have cosine squared and or sine squared? Use the power reduction formulas. Okay, so cosine squared, that turns into 1 plus cosine of double angle, 2 theta over 2. Delete, and same for sine squared, so I'm just going to copy that and turn the plus into a minus. Okay, nothing to do with the third term. Okay, so now we should do some arithmetic. Okay, so let's keep the r cubed outside. So we have 5 plus 5, and similarly we have 7 minus 7. Okay, so I want to do that because, check it out, we're going to get 5 plus 7, 12 over 2, so that's 6. R cubed gets multiplied by 6, and then how's about, I should remove all of that, how about the cosine 2 theta? 5 minus 7, negative 2 over 2, negative 1. Okay, so minus cosine 2 theta. Okay, minus 4r squared sine theta. Okay, so we are ready now to, oops, maybe not quite. Let us, no, it's fine. We can keep it factored. We can now integrate with respect to r. Okay, so we are going to get 1/4 r cubed. I'm sorry, r to the 4th. 1/4 r to the 4th. And what about r squared? That's going to become r cubed. So it's going to be 4/3 r cubed. Okay, so I'm going to erase that. Okay, quick check. Yeah, r to the 4th over 4 minus 4r cubed over 3. All right, I stopped the video because I needed to grab my eval bar from my tool belt. So we plug in r equals 3 at the bottom, r equals 5 at the top. Okay, so we'll do that into r to the 4th and into r cubed. So why don't we do the arithmetic out here? Okay, so we need 5 to the 4th power minus 3 to the 4th power. Okay, so what do we get? 544. And the same thing with cubed. So 5 cubed, oh, that's not too hard. 125 minus 3 cubed minus 27, is that 98? Yes, that is 98. Okay, so we're going to have 544. So we might as well do the over 4 as well. So with your indulgence, I will just do this. We'll get 136. And then we need times 4/3. That's not divisible by 3, unfortunately. Times 4/3, we're going to get 392 over 3. Okay, so what do we get when we fall in love? The first one is 136, and then the second one is 392 over 3. Okay, so we have that. We have paid for the evaluation. That one. Okay, looks good. I believe that looks good. Okay, so we are just about ready now to do our outer integral. I do believe. What are we going to get? So 136 has to distribute through. So again, with your indulgence, let me do the product by 6. So we have 816. 816 theta for our first term. minus 136 cosine 2 theta. So when we integrate and we have to do a little u sub, we can do that mentally, right? So integral of minus cosine should be minus sine, okay? And then we divide by 2, so 136 divided by 2 is 68, I do believe. Is that right? Yeah, 68. So minus 68 sine of 2 theta. Always good to do a mental check. Derivative of sine is cosine, so it stays minus. 2 goes out, chain rule, 68 times 2, 16, 120, and 136. Okay. And then the last term, we are going to subtract 392 over 3. Sine antiderivative will be negative cosine. So cosine theta, and that should be a plus. Is that right? Okay, derivative of cosine is negative sine. Okay, so that is good, and we're going to plug in 0 and pi. Okay, in this case, 0 is very dangerous because that goes away, sine of 0 is 0, cosine of 0 is not 0, it is 1. Okay, so yeah, that term is going to survive. Okay, so plugging in the upper end points. So we're going to get, right, so I should label. We are going to go from 0 to pi. Okay, so we're going to get 816 pi. And then what is sine of 2 pi? 0. Okay, so minus 0. Cosine pi, that is negative 1. Okay, so that is minus 392 over 3. Okay, now we plug in 0, subtract, and that is going to be 0, 0, 0 minus 0, just for emphasis. And then at 0, I said cosine 0 is not 0, it is 1. So you get plus 392 over 3. So do the 392's cancel? No. You have a minus here and another minus here. Okay, so we are going to double. What is 392 times 2? We get 784. All right, so there we go. Our final answer is 816 pi minus 784 over 3. We will erase that, and there we go. Is that a positive number or a negative number? I think it's positive, don't you? Yeah, big positive number. Okay, so that is our video for today. We finally did a double integral in polar coordinates. We are just scratching the surface. Okay, so in our next video, we are going to do some more examples, and we're going to see how to generalize this so that it's not just a polar rectangle that we can integrate for our domain. Okay, we're going to look at more general domains than that. So until next time, thank you so much for watching. Enjoy the rest of your day. Bye.